Hello, on behalf of TAS International, welcome. My name is Peter Rittmeyer. In this training we will give an overview of the MBFE contacts. We will discuss the different MBFE algorithms, specifically the kinematic contact and the characteristic-based contact. Those are the flavors available in the MBFE contacts. Let's go to the table as you have seen before. And the MBMB, you only had one possibility to choose. For MBFE, you in principle have three main contacts available. It's the kinematic one, it's an idealistic one. It means basically no penetrations are allowed. Typically this type of contact is not recommended to be used. I will explain in more detail later on. Then, just like in the MBMB contacts, you have the characteristic-based contacts. Those are allistic. But instead of only having a force, you also have a stress-based contact. Stress basically means the amount of contact force depends on the amount of contact area. And force, that's not the case. Well, let's focus on the description. You have to define an MB surface. That can be one ellipsoid or one plane, but it can also be a set of. The FE surface can be either rigid, either deformable. In case it's deformable, it's obvious that you take the contact characteristic of the master. Rigid or deformable FE have to be defined under a group FE. As already said, there are two types of contacts available. That's the inelastic contact. An example of that is given in the left XML part. You see an airbag contact to the head, and that's one of a kinematic. At the right side, you see the same type of contact, but then with a contact force characteristic. In this case, the master is considered as deformable, which also makes sense in this case, because it's the dummy, so the contact characteristics of the dummy are taken. The airbag itself, as it is deformable FE, will deform by itself by its material properties. I also showed you the characteristic.contact. If you would like to change between a force and stress, this is the place to adjust that. But bear in mind that of course they also have to define different load functions or unloading and hysteresis. Also for stress you have to define a thickness. MBFE contacts. As already said, slave surface are the nodes. The master surface are the planes, ellipsoids and cylinders. It can be a set. Bear in mind that cylinders, although visually you might think they have a finite length, are considered to be infinite. If this is hampering your situation, your model, you can make use of the following option under Xmagic, which enable you to make a mesh of the cylinder. Obvious also for a plane or an ellipsoid. But then, of course, an MBFE contact can be applied, but then you have to switch over to an FE-FE. Let's focus a bit more on the detail on the kinematic. As said, it's inelastic, so no penetrations are allowed. Well, the conservation of momentum is ensured, so that's fine. The conservation of energy, however, is not. If you go into focus, for example, on the robustness of your simulation by looking to your energy balance, you might see strains, steps, for example, or a drift which you don't understand. That might be due to kinematic contact. And that is one of the reasons it's not recommended to be used. But there's even a more important reason for which it is better not to use this. Those are the kinematic constraints. As said, nodes that are penetrating is not allowed. you will have some penetration, but in the same time step, the nodes which are penetrating are put back on the surface, in this case, for example, the master surface. Well, you can imagine that then you run already into trouble if you have a facet surface, because a facet surface is supported bodies and those nodes are not supposed to move. So you have something like what we call a double constraint. On the one hand, the contact says, well, you have to move in that direction, but the support of the facet surface says, well, no, you have to stay at that position. And for that reason, the nodes that are, let's say, double constrained are taken out of the contact. And for that reason, the contact might not be working as you would expect. This is one of the prime reasons why this kinematic contact is not preferred to be used. Another remark, which not only accounts for kinematic but also for the characteristic contacts, is the following. In this case, you see there are a lot of nodes of the slave on the master surface. But bear in mind that you have a very coarse slave surface. Then it might be that the contact is even not observed. That's not only for kinematic, but that's also for the Haar-based contacts. So for that reason, if you have very slender MB surfaces or a very coarse slave surface, you might simply go through the contact because there is no contact seen. Now let's move on to the characteristic-based contacts. As said, there are two types available, a force penetration and a stress strain. Here you see the force characteristic explained. It might look a little bit strange because you see areas, but those areas are not the areas I was mentioning like in stress. Those areas are used to distribute the force of the force characteristic over the several penetrating nodes. How is this contact working? There are a few nodes, as you can see in this example, 3, which are penetrating. The one which is penetrating the most is used to derive the contact force. This contact force then is by the equation you see at the left used to distribute this force over the several nodes. On the master MB surface, on the body, this contact force is also applied. Now let's move on to the stress-based. It's quite a long equation, but let's try to keep it simple. You see at the right that the F total is the sum of the individual forces. Well, that's different with respect to a force base. You can also see that there is an AE, which means the contact area per node. The rest looks pretty familiar to what you have seen, for example, in the restraints. You have an elastic part, a damping, which might be constant, or a function defined, and there is also a link possible with respect to the elastic contact force. Maybe of a little bit more attention is the T, that's the thickness. So per node which is penetrating, you know the penetration and you know the thickness of that specific part of the contact. Well, those together provide you with the information how much strain is there located. And this strain is used to derive the stress for that node. And that is multiplied by the area, and due to that you have an individual contact force. Here you see the summation. You see a master plane and 2 cubes. The left, that's the force-based characteristic, and the right is the stress-based contact. Let's focus first on the force. Both cubes have the same amount of penetration. However, the contact force applied is the same. This is not something you might expect from physics. But in case in MADYMO, when the penetration is more or less always in the same way, this might be okay, because it's a very fast algorithm. Also, the force penetration characteristics are easy to derive from test data, which is not the case for stress-based contacts. However, stress-based contacts, as you can see at the right, the sum of F1, F2 and F3 will be larger than if there's only just one node penetrating, because the penetrating area of the most right cube is less. Obviously, this is much more realistic, but converting this from a test or from scratch from simulations is a less trivial situation. For that reason, force-based characteristics are generally used. Let's move on to the next slide. It's about friction. You have seen probably this picture before. It's just recommended that if the relative velocity is low, you cut it down to 0. It just prevents numerical noise in your simulation. The last slides will be about orthofriction. What is it meant for? It's meant to mimic pocketing effect. Let me describe what pocketing is. You have your shoulder belt in real, which is penetrating the jacket. This jacket will deform, and therefore you have something like a pocket. And this pocket prevents that the belt is sliding in the direction of the red arrow, in this case 2. However, characteristic base has no deformation of the jacket, because it's lumped in the contact force. Well, to mimic this pocket effects, you can define friction, or even penetration, as you will see in the next slide. This friction can be defined in 2 directions. One in the shoulder belt direction, obvious, it's applicable for all contacts, but in this case we're just discussing the shoulder belt. In the blue arrow direction, you can define a normal friction function. Orthogonal, you can increase the friction. That's basically what orthotropic friction is about. If you make use of the MADYMO belt fitter, the direction 1 and 2 is taken automatically into account. 1 is in the direction of the belt, 2 is perpendicular. Here you see an example given of orthotropic function. You see the equation, and this equation is a pretty long one, but the essence is that you can define a friction in both directions, and you can even make the friction dependent on the amount of penetration. The last slide is about initial penetrations. 2 types are available, none and correct. By default it's none. It means that if there are penetrations, you will have a contact force. If this contact force, for whatever reason, is not acceptable, and you're not able to correct for that, you might use the initial type correct, which means that the initial penetrations are put to 0 at the initial state. That already brings me to the end of this presentation. Goodbye.